Yeah, hello everybody. In this session, we discuss about pin diagram of 8086. So in this pin diagram of 8086 is available in a DIP package, dual in package, and it consists of totally 40 pins, 20 pin on one side and 20 more pins on other side. And these 40 pins can be classified into three parts. So one part is common signals. So totally 40 are there. In 40, so 32 are the common signals, and eight signals, remaining eight signals can be shared between minimum mode and maximum mode. So here one need to know what do you mean by minimum mode and maximum mode of 8086. So whenever the 8086 want to works with another processor for complex applications, then the maximum mode is to be entered. Otherwise, if it want to work only alone, only one processor, then it should be worked in minimum mode. Therefore, 8 pins are useful for shading between minimum mode and maximum mode. First of all, we'll look through the common pins of 8086. If you observe here, on a left side, starting from ground pin number 1 to pin number 20, and on right hand side, if you observe, yeah, on right hand side, if you observe from 21 to 23, and then 33 to 40. So these are all totally 32 pins. The remaining 8 pins, you can 24 to 27 and 28 to 31. So these are all going to be the 8 pins which are shared between the maximum mode and the minimum mode. So if you observe here, 24 to 31 pins, these are totally 8 pins. These 8 pins are given for sharing between minimum mode and maximum mode after setting a pin calling it as min slash max bar. When min slash max bar is 1, then it works in minimum mode, and min slash max bar is 0, then it works in maximum mode. Then these 24 to 31 pins are going to be shared according to the min max pin. So first of all, we'll look through the common pins. Yeah, the common pins, first of all, you can observe the address data bus, AD0 to AD15. These AD0 to AD15 are actually the multiplexed address and data. Means the same pins can be act like an address bus and can act like a data bus also, of course based upon some other signal, based upon some controlling signal. At one condition they act as address, at another condition they act as the address. So here a nothing but address, D nothing but data. So AD0 to AD15 totally 16 bit address bus and 16 bits the data bus. Okay, that is nothing but A0 to A15, D0 to D15, D0 to D15. Okay, and but for 8086 contain 20-bit address and only 16-bit data. So 16-bit data is already available in D0 to D15. And coming to the remaining address, you can observe here. This is not AD16 actually. This is A16, A17, A18, A19 slash S3, S4, S5, S6. So here the pins are multiplexing of address and status. Earlier there are multiplexing of address and data. Here the multiplexing of address and the status signals. At one time they act as the address, at another time they act as the status. In this way totally A0 to A15 here and A16 to A19 here, totally 20-bit address. And about status signals, we'll look through next. Now, coming to the next pin, 34th pin, that is nothing but bus high enable BHE bar slash S7. S7 is another status. These BHE bar and S7 are used to access the higher order bus or low order bus, because we know that the memory, either it may be the even bank or it may be the odd bank. To select either even bank or odd bank or total bank, so these BH slash and S7 are going to be useful. BHE is an active low signal. These two are multiplexed here. Now coming to min max bar, this already said to select either minimum mode or maximum mode, and this is a read bar. This is active low read signal to indicate whether the signal is in read position or not. To activate the reading, so we should give 0 to this. This is actually the output signal. Now coming to the test. So the test signal is a very important signal. This is for testing the low speed device. Low speed device generally in low speed operation. However, the CPU is in high speed operation. So to interface the low speed device with a high speed CPU, so the we need to test that low speed device whether it is ready or not. This is just for synchronizing external activity to the processor internal operation. So 8086 will enter into wait state after executing the wait instruction, and it enter into execution when not only when the test is made low by an active hardware. Means whenever a device is ready and test bar becomes low, then the wait it convert into execution. Then 8086 no more in waiting, it will resume its execution. This is the need of test. And ready is the acknowledgement given by the low speed device that I am ready to transfer my data or get the data. So this is provided, this is an actually the input signal to the 8086. Now reset. So during operation, something happens to the microprocessor, maybe power failure, maybe the power may be in dangerous level or something happen, then we need to stop its execution immediately. Then we are going to use of this reset bus reset button. This should be active at least for 4 cycles for resetting the entire 8086 operation. Now ground. So here we are having two grounds, one at pin 1 and that is pin at ground 2 at 20. And clock. As you know, clock is not internally available for 8086. From externally it is available, and it is about 33% duty cycle, and it is also asymmetric. And because of clock we are going to have operation in synchronism with all peripherals. Next, intr is nothing but interrupt request. So whenever some device or some peripheral requesting the um, CPU for its activity, then the interrupt request is going to be raised. Whenever interrupt request occurs, then if CPU feels that that interrupt is to be executed, then it raises the interrupt acknowledgement. Yeah, one more is a VCC, that is the supply voltage. The supply voltage generally at 5 volts. Yeah, so till now we have discussed the 32 common pins that are available here, and now we'll see to enter into the minimum mode and maximum mode. So we are having 8 pins. To enter into that, one common pin we require, that is min max pin. So when min max pin, is 1, it enters into minimum. When it is 0, enters into the maximum. Yeah, let me see the minimum mode pins. That is 24 to 31 pins, which are you can observe interrupt acknowledgement, address latch enable, den, dtr slash r, m slash io bar, wr bar, hold acknowledgement. Yeah, first of all, see dt slash r bar, where dt is data transfer, data transmit, r bar is receive. So this is actually the output signal from the 8086 to control the direction of data flow through the data transceivers. Either we are reading the, we are receiving the data, or we are transmitting the data. So that can be controlled by this signal. Whenever dt slash r bar is 1, it transmit, means it allow to write the data. When dt slash r bar is low, then it allow to read the data. And den bar, that is nothing but data enable. This is actually the output signal from the processor used as output enable for the transceivers. So whenever this is enabled, then only that particular data will be enabled, that particular data will be valid. Otherwise, even though the data is available on the data bus, still it is not the valid data. Until unless den is enabled, that data may not be valid. Now coming to address latch enable. In this address latch enable, it contains actually the demultiplexer, which are going to divide both the address and the data. Really useful to demultiplex address and data from AD pins. And M slash IO bar. So the 8086 microprocessor may operate on memory or may operate on IO. So to select either from memory, either with the IO. So this pin is going to be useful. And write bar. So whenever we are writing data onto the device, this must be low. Otherwise, you can't write it. And finally, acknowledgement. So after receiving the interrupt request from the device, if 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 we know that, if CPU knows that it is to be executed, then it raises the interrupt acknowledgement pin. It is active low. Now coming to hold acknowledgement. So this hold and hold acknowledgement are especially useful whenever the DMA requires a bus. DMA requires a bus for transferring data between two peripherals. So hold is the input signal to the processor that the DMA controller requires a system bus for transfer. Okay, and when CPU feels that it is genuine, then it raises the hold acknowledgement, means it releases bus to the DMA controller. So in this way, hold acknowledgement is going to be raised. And whenever hold becomes low, CPU feels that there is no need of bus to DMA controller, then hold acknowledgement is also becomes low. In this way, bus is going to be released. So now goes to the maximum mode pins. So again, maximum mode also contain 8 pins. So let me see 3 pins here: S0, S1, S2. So these are active low. Based on these 3 signals, the operation is going to be decided. So in minimum mode, INTA bar is there. Dedicated INTA is there for interrupt acknowledgement, whereas in maximum mode, when S2, S1, S0 bar are 000, then it is going to be the interrupt acknowledgement. Similarly, whenever you are reading from IO port, this should be 001, writing to IO port 010, a no operation 011, and for accessing the code from the memory, then 100, and if you want to read from memory 101, if you want to write to memory 110, and if no need of any accessing, then it should be 111. In this way, based on these three signals, status signals, the machine operation is going to be decided. Now we are having two more signals, calling it as QS0 and QS1. These two are useful for knowing the status of the queue. So in 8086 we have a 6 byte fetch queue, right? To know the status of it, these two pins are going to be useful. So whenever these two are 0, there is no operation with the fetch queue. And when it is 0 1, so it is a first byte of an opcode from queue. And when it is 1 0, the queue is empty. And it is 1 1. When it is 1 0, meaning of that is empty the queue. And it is 1 1, so subsequent byte from the queue. So fetch or get the data from subsequent byte from the queue. So in this way, queue status are going to be decided by these two pins. And coming to the last two pins, calling it as request grant. So whenever the local bus masters want local bus, then it is going to ask the CPU by the signal calling it as request. By using request, they are going to ask the CPU to release the local bus. So once they release once CPU feels that it is genuine, then it is going to raise the grant. That is nothing but GT0. Of course, here we are having a request 0, request 1, grant 0, grant 1. So GT0, it will have high priority than GT1. Means whenever there is a request with RQ0, also request with RQ1, then RQ0 is first serviced, then only RQ1 is going to be serviced. So in this way, the 40 pins of 8086 that I discussed, which are required to understood for operation of that one. Thank you.